So in case you don't quite catch it in my tone, I think that electromagnetic radiation, sending energy the way the sun does in all different forms of electromagnetic radiation, I think that is so totally cool. But it's not just the sun. I mean, we create these different forms of electromagnetic radiation here on Earth. Let me go ahead and remind you, this is from shortest, and we use the symbol lambda for wavelength to longest wavelength. And when I start putting these up here, you're going to recognize that these short wavelength energies are the most intense and kind of the dangerous. So we have gamma rays, like as in the Incredible Hulk. We have X-rays, and then we have ultraviolet radiation, and then we have visible light. And I told you could use the Roy G. Biv to kind of remember the colors of visible light, but it's kind of backwards as I have it from left to right up here. So I'd have to go Roy G. Biv. I hope you're able to read this. Okay, where violet visible light bumps up against ultraviolet radiation. Makes sense, doesn't it? And then longer than red, we have infrared. Okay. And then longer than infrared, we have microwave radiation. And then longer than microwave radiation, we have radio waves. And radio waves, I mean, a repeating unit of electromagnetic radiation that is radio waves, I mean, you're talking kilometers. So that is just so cool. And I mention that because all of these different forms of radiation follow what I'm going to talk about now, kind of what we call laws of radiation. First off, all objects will continually ooze electromagnetic radiation, sending out this zzz in all directions, and they will actually send out their own little spectrum. They will emit radiation over a range of different wavelengths, not just one wavelength. The other thing is that the hotter the object, then if you look at the energy it's oozing, you're going to see it's oozing more energy in the shorter wavelength. Does that make sense? I think so. I guess that was 3. This one says that if it's a hotter object, it will be oozing out more radiation in general. And this one says, and that radiation in general will tend to kind of be distributed here at the shorter, the shorter types of energies. So those two kind of go together, 2 and 3. The other is that objects that are good absorbers of radiation are also good emitters of radiation. We'll talk more about that. So we use these kind of what's called radiation curves to display the kind of distribution of energies that an object is oozing out. It may not seem like it, but actually, as you're sitting there listening to this, you are oozing out kind of an assortment of energies, probably clear down here in infrared radiation. So these curves I'm going to show you are 2 objects, and see what you think. Notice that here we have along the x-axis wavelengths, and here we have the shortest wavelength, and here we have the longest. So over there, over here on, should be your left too, right? Over here on the left, we have the most intense energies. Over here on the right, we have the least intense energies. So here we go. Here's our 2 curves. So for instance, if we were to kind of look at all the energies that the sun is sending out in all directions, we would see that it is sending out, oh, by the way, along the y-axis is what is the intensity at that wavelength. Wavelengths differentiate different forms, different types of electromagnetic radiation, and then the higher it is, the more intense it is for that particular wavelength. So here is a radiation curve of our sun, and our sun and the Fahrenheit scale is about 10,000 degrees Fahrenheit. So compare that to the signature, is what it is, of basically what is our Earth oozing out into outer space in all directions. And notice that it is shifted over here to the longer wavelength. And notice that it is squattier. Okay, so it's kind of like laws 2 and 3 on the previous slide that I showed you. Okay, it's squattier. Why? Because notice the temperature, 59 degrees Fahrenheit instead of 10,000 degrees Fahrenheit. And it's shifted over here to the longer wavelength. By the way, we do use this technique to actually gather we create a curve from a star, and we can kind of use a fingerprint and see what the temperature of the star is too.